Hey class, you've got your quiz on Monday, so I wanted to get these videos out for you. This is going to be the answer key for the first homework, the principle of parallel slices and Cavallarius Principle. So here we go. Take a look at number 1. It says that the area of the rectangle is 50 cubic or square centimeters. So they want to know what's the area of the parallelogram. And there's no numbers here. You don't have anything to go on. Maybe this base here is 5 and this height is 10. That would make 50, wouldn't it? And so they're telling us here this is 5, then this would also be 5. The height would be 10. So wouldn't the parallelogram have the same area? Well, that's true. But there was another way we were supposed to get at this. We were supposed to use that thing, the principle of parallel slices. Why didn't that work? Clear annotations. Okay, so the principle of parallel slices says that at any level here, I can take a slice. Take a little blue slice here, and then continue over to the parallelogram, take a slice at the same level. And I know that those two slices are the same length. If I go up a little bit, I can take a green slice and then continue over into the parallelogram here, take a green slice, and those two slices are the same length. I can continue up to here, take a pink slice, continue over to the parallelogram, take a pink slice, and they're the same level. And so when that happens, when all of these slices are the same length, that guarantees us that the two shapes have the same area, which means that if the rectangle is 50, then the parallelogram is also 50. And on the quiz, I would expect you to be able to answer the how do you know by saying something about, the principle of parallel slices. Exclamation point. That's it. Hopefully that idea makes sense to you guys. So for the second one, it says, do you agree or disagree with the following statement? Cavallarius Principle cannot apply to the solids shown below because their bases are different. First of all, pay no attention to the fact that there's that one gray shape. That gray side is not supposed to be the base. So if I turn that off, so to speak, then we would go ahead and say that the base of that there prism, I don't know what it's supposed to be, square, rectangle, I don't know, but the base would be the bottom, and the base of our cylinder is this circle. And the idea of Cavallarius Principle again was very similar to what we just talked about here, where we took slices, and the slices of these two-dimensional shapes were just line segments, and when they're equal, the areas were equal. Well, as I take slices of these 3D shapes, I would get a circle as I slice to this. I would get a square as I slice through this. And those two squares, if they have the same area, then Cavallarius Principle applies. It doesn't matter if they're the same shape or not. They just have to have the same area. That's what we talked about in class a bunch. I could take another slice up here near the top. I'd get a circular cross-section. I could take another slice over here near the top of the prism. I'd get another square cross-section. And again, all that matters is that the green circle and the green square have the same area. So for this question, we should definitely be saying that we disagree with this statement, because they're essentially saying Cavallarius Principle can't apply because the bases are different. But that's not true. You would want to say something about as long as the cross sections had the same area. Cavallarius Principle will apply. And that's it. Cavallarius Principle doesn't care about the shapes of the cross sections. It just wants the cross sections to be equal. The red has to equal the red. The green has to equal the green. And furthermore, we don't even need all the cross sections to be the same. Cavallarius Principle would apply even if you had a cone and a pyramid. And what I mean by this is if you had a cone and a pyramid, then these cross sections down near the base would be kind of big, and if they would be equal, the red would equal the red. As I took a cross section up near the top though, my cross sections would be small, but the cross section at the top of the pyramid would also be small. So the green would be the same as the green, the red would be the same as the red, but I'm not saying they're all the same. I'm just saying that every pair of cross sections is the same. So here's a medium-sized cross section in blue. Here's another medium-sized cross section in blue. And again, they're equal. So green equals green, blue equals blue, red equals red. That's all that matters for Cavallarius Principle to apply. And again, I'm over-explaining this, I'm sure, but hopefully you guys understand. Moving on. Number 3 is exactly what I was just explaining about these cross sections being the same. So it says the first solid shown below is a right square pyramid. This base here is a square. That's all they're saying. So that's a square. Right angles, equal sides. The second solid is an oblique trapezoidal pyramid. So we see the base here as a trapezoid. And remember, the oblique means it's slanty. So instead of this thing standing straight up and down, it's kind of pulled off to the side, right? At any height, the cross sections have equal area. Aha. That's the main thing for Cavallarius Principle. This green equals this green. And it says at any height. That's true. So again, it's saying, even if we drop down low and got this big red square, and if we drop down low and got this big red trapezoid, well, the red would equal the red, just like the green equals the green. So finally, they're saying this guy here has a volume of 400 cubic units. And then they're asking, what's this guy's volume? And well, since Cavallarius Principle applies, it would also be 400. And that's it. Moving on. So what are we saying? 400 cubic units. How do you know? Cavallari. That's it. Next. All right, so finally now we're actually doing some math. It says find the volume of each of the following prisms. So as we always are going to do, we write our formula. Then we plug a formula into our formula. So instead of B, we plug in the formula for the area of our base, which is a rectangle, so that's base times height. And we're still multiplying by height, the height of the prism. Now we substitute. So the base and height of the base, this side length here is the base of the base. This side length here is the height of the base. And then the height of the prism is going to be the perpendicular distance from the top of the prism down to the bottom of the prism. And since this prism is oblique, we have to measure straight down to the base. So we have to almost imagine extending the base outwards and calculating that distance. But 8 will be our height. So we plug 8 in for H, and we plug 10 and 10 in for the dimensions of the base. And so that gives us a base whose area is 100, multiplied by the height of the prism, which is 8. You get a final answer of 800. And all these units are centimeters, so we're talking about cubic centimeters. So that's A. We can do B. So looking at B, this is where we started to start seeing some weirder ones. So for B, the base of this prism is going to be this trapezoid right here. Yep, that guy there. And I want to highlight this. So let me fill that with, I don't know, gray. And make it just a little bit see-through. But it's that face there, that one that I'm highlighting, right? That is our base. And the reason why the base is not the bottom, I know you guys want to think the base is the bottom. So let me do this same trick one more time. Oh, that's wonky. I'm going to try that again. It is not so easy to draw a straight line, but that's pretty good. Okay, so again, let me drag this mess over here, fill it up with gray, grab that gray, make it see-through, drop it here. Alright, y'all want to think that's the bottom, right? I'm sure you do. But that's not the bottom, because if that was the base, right? Every prism has to have two bases. And so if I copy that and paste in a new one, that's not the top. To make the top is way smaller than this bottom, right? We can see that. They're not the same. And that's the main rule for a prism, is that the base has to be parallel and congruent to somebody else. Now let me copy paste this. Control C, Control V. Look at this. There is another base right back there. Those are my bases. There's two of them, and they're congruent and they're parallel. And my prism is formed by connecting the corners. Look at this corner of the front and look at this corner of the back. You connect them, and that makes our prism. You connect this corner to this corner. You connect this corner to this corner. And you connect this corner to this corner. And what that does, of course, is just creates all these rectangles going around the outside. This was a big idea. I spent a lot of time trying to explain this in class, so I hope you see it now. But you don't have a prism unless you have two of these congruent faces, right? And so that's our prism. Again, I don't know. Let me show you one more time just how you're supposed to connect these. And that's literally how this three-dimensional figure is formed, is you take these two congruent two-dimensional figures and you hold them in space and you connect the dots and you end up with a 3D shape. Anyway, that's my last chance to try to explain this to you. Hopefully you got it this time. And again, maybe you already understood it. I don't know. But let's actually do the math now. The long story made short is that to actually do this problem, you need your formula. Volume equals base times height. Well, like we just said, our base was this trapezoidal face right here. So that means capital B needs to turn into the formula for the area of a trapezoid, which is 1/2 times B1 plus B2 times H. And again, that still needs to get multiplied by the height of the prism. So there's another H over here. This H is part of finding the area of the base. This H is part of finding the volume. Alright, so anyway, what's what? Well, in a trapezoid, the bases of the trapezoid, the B1 and the B2, are these two parallel sides. So I would say B1 is this short dimension, B2 is this longer dimension, and of course B1 is going to be congruent to the 2, so that 2 from the back, we can slide that forward. That's our B1, so we can take those values and substitute them in. So we can see we're doing 1/2 times a 2 plus an 8. Now we need the height of the trapezoid, and the height of the trapezoid is always going to be that straight up and down distance between the two bases. And again, that dimension we're going to grab from the 5. Again, we could drag this 5 forward, and we can see that this dimension here on the front face is the same thing. That's also 5. So you can plug in the 5 for little h. Then you need the actual height of the prism, and the height of the prism is going to be the distance between the two trapezoids. So you can pick any two corners and connect them. That distance there is the height of the prism. Again, it doesn't matter that that distance is up and down. Heights don't have to be up and down anymore. Heights just have to measure the distance between the two bases. And again, this dimension here is obviously the same as this dimension that goes from here to here, which is the same as the dimension that goes from here to here. Any line segment connecting corners of the bases, that's going to be the height. And so we can see it labeled here as 6. So in goes 6. We now have all of our parts. So one rule is anything that's in parentheses, you got to do that first, of course. So this will be 1/2 times 10 times 5 times 6. Now for problems that have 1/2 in them, you can either save the 1/2 to the very end, multiplying all of this. You'd get 50 times 6, so that's 300. Then you could take half of 300 to get your 150. Although I typically like to take half of just one thing. You don't take half of everything. Sometimes people think they're supposed to take this and distribute it onto every single thing, but you only distribute over pluses and minuses. If we had 1/2 of the 10 plus the 5, and you wanted to distribute, well sure, you could distribute the 1/2 onto the 10 and the 5. But with multiplication, you're only supposed to take half of one thing. So find something even and take half of it, like the 10. Half of 10 is 5. So you know that you now have 5 times 5 times 6. And 5 times 5 is 25, and 25 times 6 will give you the same 150. So you guys have a little bit of options here as terms of how you want to think about this. It seems like a lot of people were comfortable just doing all the math with all the numbers and dividing by 2 at the end. If that's what you want to do, go ahead. Some of y'all might be more comfortable just doing these numbers sort of one at a time. Take half of 10, that's 5. Then multiply by 5, that's 25. Then take 25, multiply by 6, that's 150. Either way, you see we're getting the same answer. Okay, moving on. So this guy says, a rectangular prism with a 6 centimeter by 7 centimeter base has a volume of 378. Find the height. All right, so for this you might want to draw. So I'll get my drawing going. Where's my little parallelogram drawer? Here it is. So to draw a prism, ooh, that's not what I was going for. Okay. So for a prism, you draw yourself a parallelogram. That's going to be the top of my parallelogram. Now, if I'm a prism, I need another one that's congruent to it. So I'm just going to copy it. And then what you do is you take this guy and you imagine dropping it straight down. And then what we're going to do is connect the corners. And that's going to give us a good looking 3D shape. We just drop straight down to the corner, straight down to the corner. And these aren't lined up quite right, so let me just fix that. Okay, that looks better. But that's how you draw good looking 3D shapes, is you just draw the top and bottom, making sure that they're congruent and parallel, and then just drop straight down. Look at that, perfect, right? Now it says that the base, rectangular prism, yeah, so 6 by 7. All right. So whatever, this looks like the shorter dimension, I'll call that 6. And this looks longer, so I'll call that 7. The height is what we don't know, so I'll call that h. Anyway, let's do our work. We always write the formula. Volume equals base times height. Then we plug a formula in for the base. Our base is a rectangle, so that's little b little h times height. Now we start to substitute values, and just remember that for this problem, we already know the volume. So we can take 378, plug it in for V. And we know the dimensions of our base. They're 6 times 7. So we can plug in the 6 and the 7. And now we've just got an algebra problem where we're solving for h. So take these numbers in parentheses and just do that out. That's 42 times h. And that equals 378. So to solve using algebra, I just have to divide by 42 on both sides. So h is going to be, well, whatever this is. I don't know what it is, so I need my calculator. So let me pull up a calculator. There we go. And to use this calculator, clear everything out, and then I'm typing in 378 divided by 42. And I'm getting 9 apparently, so that's our answer. Now the one thing left is our volume was cubic centimeters, but our length and width, or our base and height, was single centimeters. Not cubic centimeters, not square centimeters, just centimeters. So our height should be centimeters also. It's not going to be cubic centimeters, because the only thing that'll ever be cubic centimeters is volume. Okay? And the only thing that'll ever be square centimeters is area. So the height is the length, it should be in plain old centimeters. Hey, that's it. That's the whole homework assignment, apparently. So hopefully that made sense. Let's move on to the next assignment, which will be a brand new video. So I'll see you later. Goodbye.